So good morning. It's nice to have this gathering of colleagues with various shared interests. Nice to have Itamar here giving the Chandrasekhar lectures. And so I want to tell you today about something that we've been doing in earnest over the last 8 months or so. I'm going to present, beyond the introduction, the work as we have sort of developed it, and I think we are at a stage where we have something nice to tell, so I would welcome your feedback, beginning with what would be a better title than this. I think this is a descriptive but rather boring title of the work I'm going to describe. Okay, so so I'm going to say very little about, by way of introduction, about structurally arrested states, but just to get this going in proper order, I'll say something. By way of introduction, largely I'll say things about jamming in sphere packings, different aspects of which that are relevant to my talk. And the third and the fourth bullets are actually what is the main part of the work that I'll describe. So we've been looking at the geometry of void space in nearly jammed in sphere packings in other contexts as well. And one of them has been to look at what happens to the void space in sheared sphere suspensions. And this leads us to say something about shear jamming. And right towards the end of my talk, I will talk about frictional spheres, but the rest of it is all frictionless, and that's actually sort of the interesting element of the work. Okay, so what we're going to be doing is to generate jammed structures, computationally jammed or sheared structures, I should say, through a range of distinct procedures, and we study the properties, in particular the geometry of these structures. Okay, that's what we're going to be doing. This work is mostly done by Vinuta, who is busy having breakfast right now, along with the rest of my group. But she was up late last night helping me get the talk together, so at least she has some excuse. But some work that I'll refer to also is sort of a recent collaboration with Bulbul Chakraborty, Sumantra Sarkar at Brandeis, and Momita Maiti and Klaus Heusinger in Göttingen. Okay, so brief introduction to structurally arrested states. Many substances exist in long-lived states other than the equilibrium state, and this I refer to as structurally arrested states. Glasses, gels, jammed granular matter are some examples. And taking the last example, there has been a long history of studying granular matter, which is made up of particles which are meso or macroscopic, and therefore whose assemblies are athermal in the sense of thermal energies at ambient temperatures not being relevant for their properties, and they possess interesting properties that are not typical of thermal condensed phases, though one continues to be interested in making analogies to understand what is a common description between these athermal and thermal systems. And a lot of the interest in looking at granular matter is focused on the properties that relate to the transition between flowing and arrested states. Okay, and that's also going to be my interest. And in terms of the history of what I want to describe, this goes back to the pioneering work of Bernal and various other people who unfairly get left out because it's long enough ago that those people are not around to say I did that. So Scott, for example, is actually somebody I should have mentioned who actually did the experiments early on to get these random close packing and loose packing densities, which I'll talk about, but at the suggestion of Bernal, so I think it's fair enough to give Bernal the primary credit. So the interest that Bernal had in looking at packings of spheres was to understand the structure of liquids, though that turns out not to be sort of the primary outcome of this exercise. And he used various models, including packings of ball bearings, which were subjected to various sort of equilibration procedures or shaking down to obtain close-packed arrangements. And among the arrangements of spheres or packings of spheres that were obtained were random close packing of particles at a volume fraction of about 64%. And this is sort of the object of a vast body of study. But in this series of work, there was also another sort of limit to a random aggregation of spheres that was studied and observed, which is called random loose packing. And this happens around 58%. And in some controlled fashion, you sort of got packings with these as the limit densities. And there's sort of been some expectation that this 64% is because it is something that you get by right. I already told them where all you were. Okay, so there's some expectation of this value being universal, and but there's no, I would say, universal or a common understanding of where that might come from. On the contrary, some work, including work done by Pinaki with Ludovic Berthier and myself, show that in fact the jamming density is something that you can vary systematically and understand in relation to liquid state properties or fluid state properties in hard sphere fluids. But that doesn't exclude the possibility that among that range of possible densities, there is some uniqueness to the random close packing density. Okay, so here is sort of for orientation the hard sphere phase diagram, and this is a picture from one of Bernal's papers where you see that ball bearings assemble possibly into close packed regular arrangements, but also possibly into random close packed arrangements, and the density of the close packing is about 74%, random close packing is about 64%, and I want to sort of throw into the middle of this another density which has already come up, which is the glass transition density, which other sort of set of experiments and studies expect to happen around 58%. Further down, you have melting at 54.5 and freezing at 49.4. Okay, that's sort of just the numbers for the hard sphere system to remember, and I'll be making reference to that. Okay, now jamming has been studied in relation with other forms of structural arrest in an attempt to understand sort of a universal jamming phase diagram, and Liu and Nagel many years ago proposed that one might start by focusing attention on what they call the J point, which is the density at zero temperature and applied stress, at which a collection of spheres will become jammed as a starting point to sort of understand the overall boundary. Yeah, and so this is also roughly how we are going to go. Yeah. Right. Okay. I was going to come to that down the road, but what I want to do now, the reason I'm showing this is there are a number of known properties of jammed configurations of spheres as you approach this J point, and I want to sort of talk about that, and then I want to compare it with what we're going to be talking about, right? Okay, so let me not necessarily go through all these. when we talk about jamming, there are different ways in which you can talk about it. Jamming of an individual sphere is a situation where it cannot be moved without the neighbors being moved. This you can call, and if all the spheres satisfy this condition, you would say that you have local jamming. But you also can sort of be stricter in your criterion and say that any locally jammed packing in which no subset can be moved together continuously is what I call collectively jamming. So in other words, there should not be any collective degrees of freedom which allow the system to be unjammed. And in addition to collective degrees of freedom, one can also think of global changes, such as a change in the shape of the box in which I have my spheres. And so strictly jammed is when none of these will allow you to unjam your system. Okay? And okay, so in the literature there are a couple of computational methods by which jammed packings have been generated, and one of which is the Lubachevsky-Stillinger procedure, where basically you do hard sphere MD, molecular dynamics, but as time goes on you grow each of the spheres at a given rate. And as you can imagine, as a result of this, at some point you will not be able to move any of the spheres for any finite distance, because the collision frequencies will diverge. And this situation where the collision frequencies diverge is what you call jamming. And there is a sort of an important parameter in this procedure, which is the rate at which you grow the spheres. Okay, and okay, so we will actually make reference to that later on. The other procedure that has been discussed by O'Hearn et al., starting with O'Hearn et al., is to actually think of spheres that are soft spheres, so they're not strictly infinitely repulsive below the size of the particles, and you sort of treat these systems as you do any other sort of potential for a fluid or a solid, and you sort of look at energy minimum structures. So the difference is, because there is a strict cutoff to the interaction potential, below a certain density your energy minima are all having zero energy, and so you look for the highest density at which your energy minima have zero energy, and you define that as your jamming point, and you can then look at what happens if you compress a system above the jamming point or decompress below. Okay, and so what we are going to be doing, which is sort of not these typical things, is to look at shear deformation of soft sphere configurations to obtain steady state configurations that we then analyze. So I mention it here, I'll say more later on. Okay, so we use all of these procedures. So here is sort of a list of some characteristics of jammed configurations that have been looked in the literature. 4 different quantities: pair correlation function singularities, coordination number, force distribution, and free volume distributions. These features for jam packings I will now describe. I don't know what I had in mind writing this text. And later on we will talk about the corresponding features for sheared steady states. Okay, so this is sort of a schematic, not very clearly visible, of how one defines the radial distribution function, which I'm sure is familiar to all of you. You look at the probability of finding a neighbor at a distance r relative to the probability expected for an ideal gas, and in a fluid, this is now showing the hard sphere fluid at around the freezing density. The pair correlation function looks like so. If you look at the same pair correlation function for a jammed assembly of spheres, it looks rather different. So in addition to a delta function at contact, which corresponds to the neighbors which are holding each of the spheres strictly in place, you have a near contact singularity, which I'll mention a little bit more, and you have a split-second peak which is singular with the two peaks corresponding to arrangements of particles that are shown here. Okay, so the near contact power law of GFR, I show here a log-log plot comparing again the fluid near the freezing density where this power law levels off, or sorry, the GFR levels off versus very close to the jamming point where you see this power law singularity. This is apart from the delta function that arises at contact, okay? And this is sort of being looked at as a characteristic of jammed configurations.
Right?
Sorry?
If the balls are not the same size, say a binary mixture of
right.
sizes, this double peak will disappear?
The partials
partials you will get it. You will get it. It is, yeah. So, yeah. I mean, I'm not sure what happens if the sizes become very different, but certainly for the typical kind of binary mixtures you see, you will see, you study, you will see it. And like I said, it is a matter of just what the local arrangements are. Yeah. Okay, so another characteristic of jammed configurations is the coordination number, which is how many neighbors you have in contact with you. And these are all sort of the first set of experiments to determine this, which had these steel balls sort of dipped in ink and dried off, and the dimples are all the contacts, so that's how you count them. And so you have for the hard sphere jammed systems a distribution of coordination numbers that is like what is shown here, with the average value as well as the most probable value of 6, which is 2D, which is the number of constraints you need in order to have, you know, each degree of freedom constraint so that you have jamming. And this number is what you see. In the presence of friction, which I'll come to later on, the relevant number is d plus 1, okay, which would be 4 in 3 dimensions. Okay, so yet another characteristic of jamming is the force distributions, and I won't say too much about this either now or later, but basically the presence of a finite force peak is seen as an indication of jamming in packings. Okay, so the last one, which is the free volume distributions, I'll say a little bit more because this is stuff we have been doing. And so one way of motivating this is to ask the question, which somebody did, I'm sure, some time ago, whether we can tell apart a liquid from a jammed configuration by looking. Okay, and here are 2 snapshots, and normal looking will not do, but we can look in other ways. And one of the ways that we have explored is to look at the empty space in sphere packings, and free volume in particular is a good way of characterizing empty space in sphere packings. And we ask whether it's useful to understand the geometry of jam packings and amorphous order. A few definitions first. So the free volume of a sphere in a sphere packing is the volume over which the center of a given sphere can translate while all the other spheres remain fixed. Okay? So here is an illustration in a liquid-like configuration where this red sphere can move, or the center of this red sphere can move in the shaded blue area without overlapping with other spheres. And this blue area shrinks to a dot when you look at jammed configurations because each sphere has neighbors which are holding it strictly in its place. And for slightly unjammed configurations, you would have, or you expect to have, a localized volume whose dimensions are given by the degree to which you uncompress the system. Okay? Okay, so I won't go through this slide because I do have to keep an eye on the time. Is that correct, by the way? Okay, so that's 5 minutes. So I should stop when that's at.
At 10:05. Sorry. 10:05 you should stop.
10:05 I should stop. Okay, very good. That's easier to. Okay, so it should actually be set 5 minutes fast so that you stop when the time is up, and then you have 5 minutes for questions. Right. So, okay. So anyway, so there is an algorithm by which the free volumes for polydispersed sphere packings can be computed to arbitrary precision, which we use. And when you look at liquid-like configurations, this is the free volume distributions that you get. They have some generic form with the mean shifting to smaller and smaller values as you go to higher densities. And then you can ask, what happens if I now zoom to much higher densities? This is all sort of around freezing to melting densities. So I can ask what happens if I go to much higher densities so that I'm very close to the jamming point. Strictly at the jamming point, the free volumes are 0. But if I decompress ever so slightly, I should have a finite free volume distribution, and there will be a mean value, and I can ask what should it look like, and sort of one expectation is that it will basically look like this with the mean shifted to very small values. But that is not what you find. Here is the free volume distribution that you find for nearly jammed sphere packings, and this is for comparison how it looks like at the freezing density. And one feature that sort of emerges out is the presence of a power law tail, okay, and with an exponent which we don't have a very good explanation for at the moment. And
I mean,
I guess people will give you enough trouble when all these things come with error bars and so on, and there are systematic errors.
I mean, because they have a function, why did you focus on that?
say that
You have a rather complex function, why did you focus on
Here?
on that part?
right. Well, no. So
Why not on the upper orchestrated?
no. So everybody is free to choose their pet problem, right? So I'm focusing here. This is possibly because it's not a feature that you see in the liquid free volume distribution, right? Right. So, I mean, one can imagine that, in fact, this is also, it turns out not to be true, but one can sort of see this feature as being sort of an analytic continuation of the liquid-like free volume peaks, but that, in fact, like I said, that's also strictly not true. You can see that this tail of the peak is already broader than what you have in the liquid-like distributions, but I'm not going to worry about it too much myself, okay?
First up to
but,
-12
sorry?
you can fit with the Weibull.
Say that again?
First part you can fit with the Weibull distribution, like
Haven't, we certainly haven't tried, but I haven't thought about this. But Rahul, the answer to your question is the geometric problem has no error bars. You give me a sphere configuration, I calculate the free volumes with arbitrary precision. Okay? Then it's a question of how many configurations do I average, or in order to say that the free volume distribution at a given density looks like this. And that we've done enough, but if you ask me error bars, I don't have them at the moment, but that's easy enough to generate. Yeah.
This is for a certain size ratio, right?
Sorry?
This is for a certain
This is now
This is not bidispers.
single component. Yeah. Okay. So now one thing that this observation, where this power law tail comes from itself is an interesting question which we have spent some time on unsuccessfully to study. So anybody who has ideas on how one might explain this power law tail is welcome to talk to me. But one of the other questions that we have looked at is, if this is a signature of being close to a jamming point, is this something that I can use to look at jammed configurations in other contexts as well? Does it serve as a signature for being close to jamming in other situations? Okay, so what those other situations could be a number of things. It could be looking at jamming in the presence of attractive interactions, in the presence of pinning disorder in the system, in the presence of shearing, which is the example that I'm going to spend the rest of the time on. Okay, so, okay, but before I do that, yeah.
You don't expect the power density to increase as you go further close to the
You do expect. So yeah, so basically, you know, this feature here sort of rides on the power law and keeps going to smaller and smaller values the closer you get to the jamming density. So, say that again? So the only numerology I can offer for this is it's twice the exponent for the pair correlation function, singularity, roughly. But we've tried to
It's a half of 1.8 or something.
no, but
So I think what is going on is nominal.
say that again? This,
You have to have a cutoff.
there is a cutoff. No, there is a cutoff. No. So, okay. So the free volumes, you're going close to the jamming point. They get smaller and smaller on average, right? So, but this tail roughly remains in this range, but it has a cutoff, right? But you know, if you sort of make the right transformation of variables, you can sort of, in scaled variables, you can see the range of this power law diverging as you go to the jamming point, right? But there is no divergence of the mean free volume. It's actually going to 0. Yeah. Okay. So before I go on to sheared sphere packings, a couple of more things to say in terms of the general background. One is that from the free volumes that we calculate in this way, we can calculate an equation of state from a geometric hard sphere equation of state that relates the average free surface to free volumes to the pressure in the system, and so we do that near the jamming point, and so here I show the inverse pressure as a function of density, which is going to 0. I think this is for bidiscrete. Yeah, it says so. Yeah, and there is an expectation that the deviation from the 0 value should go linearly with a coefficient that's given by the dimensionality of the system, and this turns out not to be the case, and that has some relation to the shape of that small part of the free volume distribution, but let me not spend time on this. But the thing that I want to focus on is that this nearly jammed or the close to jamming equation of state intersects the extrapolated liquid equation of state around 56%, which is close enough to the literature value of the glass transition. Okay, and if this combination of pressures
What is this glass position? What happens?
that's another talk. I'll say what I can about this density. I'm just pointing. No. Yeah, but I'm just telling you that here are all the things that one should keep in mind. Yeah. So I mean, this number. Yeah.
It's arbitrary.
No, this number comes from the Pusey-Van Meegen colloidal glass transition experiments, okay, and many other places. But one thing, if you want me to be concrete about, I'll tell you.
For bidiscrete, the number is different.
See, these numbers will not be exactly the same if you depend. Yeah, but it's close enough that you. Yeah. So no, that's why it doesn't bother me that it's 56 versus 58, right? But okay. Now. So, couple of other things. Again, you know, I'm sort of talking about phenomena, giving a couple of examples of what happens in this range of 55 to 58% that people have been interested in. And one of our goals is to be able to eventually say something concrete about these phenomena. I understand. Yeah, so one is the random loose packing as studied experimentally by these guys, and the onset of dilatancy happens around 55 to 56%, as you see here. And this is also a density range where other people have looked at shear thickening yeah. So the question is, can we say something about the structural origins of these phenomena? Okay, so here let me come to what we do. So what we do is to look at shear deformation of sphere packings over a wide range of densities, and this is wrong, it's soft spheres, and we look at the evolution of the structure as we increase the strain on these systems, and finally we look at how the steady state sheared configurations behave when we subject them to jamming protocols of various kinds. Okay, so now as I said, the context for our work is shear jamming, and here is sort of a quick summary. This is the stress density phase diagram for frictionless spheres, where you have jammed jammed states on the right hand side and unjammed states on the left hand side. It has been proposed by Bob Beringer, Bulbul Chakrabarty et al. That in the presence of friction, which is what they study experimentally in Beringer's lab, you extend this phase diagram to include densities that go far below, and so there is sort of another limit to jamming, which is the limit to shear jamming in frictional systems. And one of the goals of current work is to understand what this range is and where does that come from. Okay, sorry. Okay, so what we are doing is looking at monodispersed soft sphere systems, which we obtain in a range of about 0.45 to 0.64 by either compressing fluid configurations or decompressing the jammed configurations that we have generated using the standard protocols. We do athermal quasi-static strain, that is alternating strain and energy minimization till we reach a steady state. Okay, and so here is what we get in terms of structure for our steady state configurations. What I'm showing here is one density as a function of the strain as it increases from 0, and here is the number of contacts or the distribution of the number of contacts, and what you see is as the strain increases, this distribution moves to the right. Okay, from having 0 contacts, I begin to have a finite number of contacts, and the green curve here is the isotropic jamming curve for reference. Okay, similarly the pair correlation function, which looks like so, something wrong, yeah, which looks like so at the starting point, develops in the manner that I've shown till the magenta curve, beginning to look like the isotropic jamming curve. The pair correlation function likewise starts out looking liquid-like, which it is, and at the end of the day has developed a power law tail in the steady state, just like the isotropic jamming case. Okay, and similarly the free volume distribution starts out liquid-like, ends up looking like jammed configurations. This is at 58% volume fraction. Okay, so fine. We'll continue. Now I show you the mean coordination number as a function of strain for a whole range of densities. What you see is this behavior, that the mean coordination number rises and reaches a steady state value, and that steady state value is increasing as I increase the density of the system, approaching 6 in the limit of 64%. So here is the distribution in the steady state of coordination numbers. Again, you yeah, didn't come at the right time though. This is not where the kaboom is. But okay, so the distribution, as I vary the density in the steady state, is moving towards the distribution of the jammed configurations, but more importantly, there is a mean coordination number that's increasing, right? And the pair correlation function, as I already showed, has this singularity at 2 sigma already at very low densities, and it develops a clearer and clearer cusp also at the smaller value of a square root of 3 as I go to higher densities. Okay, pair correlation function, power law tail for all the densities I observe, and similarly the free volume distribution has a, power law near contact distribution for the pair correlation function, and a power law tail for the free volume distribution for all this wide range of densities. Okay, so structurally, as I shear a sphere packing, even at densities lower than the jamming density, isotropic jamming density, I develop features that make them look jammed. Okay, the question is, are they really jammed? And you know, for frictionless spheres, they shouldn't be, but is this telling us something? Yeah?
Can you say in your AQS protocol, you have boundary conditions, or?
Yeah. Okay.
So it's always a square, you know, it's coming back, right? You do the usual.
Yeah.
So you don't really change the shape of the box.
Well, we do change the shape of the box.
But the other boundary conditions.
Well, Lees Edwards.
Lees Edwards.
Right. Okay. So, so what I want to suggest as the answer to this question is that there is an interesting connection to frictional jamming, and now I want to say why we think so. First indication is the mean coordination number against density. The black dots are our data, and the green dots are data from frictional sphere simulations by Leo Silbert, and the red curve is some theoretical estimate. The main point to note is that the mean coordination number as a function of density that we get is very close to what people see in frictional simulations, even though we don't have friction. Okay, same behavior seen in 2 dimensions. Let me skip that. Then we said, okay, so these are looking jammed, these configurations, so let's sort of subject them to a jamming protocol and see what happens. And the quick summary of what happens is that if we do the jamming using Lubachevsky's slinger slowly enough, we go to 64%. Okay, but as we do this faster and faster, right, we begin to see a non-monotonic dependence of the jamming density on the initial density of the sheared steady state configurations. And interestingly, that non-monotonicity indicates a special value of 56% or 58%, depending on which axis you're looking at. Okay, so there's something changing around 58%. And if we look at the force distributions, yeah, remember what I said, that this is sort of used as an indication of being in a jammed-like state, and we see that across 58%, these upper curves have simply been shifted for clarity. You go from a situation at low densities of not having any distinct finite force feature to one where you do, all below jamming without friction. Okay. Okay, so then we said, okay, let's look at a geometric criterion for when I might have jamming in these systems, right? One way of doing it is to sort of pick all the particles that are locally jammed, which we define as having more than 4 neighbors, equal to or more than 4 neighbors, and we do bootstrap percolation to find the particles which are locally jammed surrounded by other particles which are also locally jammed, and we look for percolation of these particles, and we find that there is a percolation transition around 54%. Okay, then we said, okay, so if we have these structures which essentially look jammed, but for the fact that there is no friction, what happens if we were to take these configurations and we add friction, right? So there's sort of different ways of doing it depending on your degree of realism. The simplest thing we said is, let's sort of imagine that given that I have a contact network, at each contact I have a restoring force to the transverse displacements. Let's look at what happens to the soft modes in the system if I were to add this, right? And what we find is that above Actually, I'm not sure about this number, but okay. Well, the data is there. Above 54%, certainly above 58%, no soft modes are left when you apply a transverse restoring force.
Soft modes being conventional modes?
So yeah, you take the configurations, you have your compressional potential, the harmonic potential, you add a transverse spring and you do the normal mode analysis. But more, I think, to the point, we take these same configurations and now we treat these as spheres with friction, right, using some elaborate model. I won't go through the details because I'm just about out of time, but what we look at is for each density, by varying the friction constant, we ask whether the configurations remain stable or they don't. Yeah? And we monitor this by looking at the stress and also by the coordination number. And you see that for this particular density, for small frictional values, the stress decays to 0, and so does the coordination number. Whereas for high enough frictional values, the stress remains finite, the coordination number remains finite. Whereas at a low density, this is sort of borderline. For all the frictional coefficients, stress decays to 0, coordination number decays to 0, and we can sort of make a phase or make a plot of the threshold friction coefficient as a function of density for our structures. This graph simply showed that the structures remain intact, but I'll come to that if I need to. And what you see is a dependence of the friction coefficient from our steady state configurations, which compare very well with Silbert's friction simulations. Okay, so here is a summary. Sheared friction, late night. Frictionless soft spheres develop structural features akin to jammed packings in a wide range of densities below RCP. Contact number, force distributions, and force network percolation indicate stable structures above a packing fraction of 58%. Local stability analysis and frictional simulations show stability above packing fraction of 58%. So the conclusion is shear induces structural features that can generate jamming in the presence of friction above this packing fraction. And why is it interesting to sort of do it this way? It's a very complicated way to look at the problem. I think being able to say something about what happens in some well-defined procedure without the presence of friction can be a very useful handle to understand a variety of phenomena where you have jamming at densities below the isotropic frictionless jamming point. Thank you.
So we have time.
I have one question. I mean, you use strain in your phase diagram. Strain is not a state function. So why do you use strain? Strain is a bad quantity to use in theory, right? Stress is a state function. Strain depends on, reference states, etc. So what's the meaning of these plots as a function of gamma?
So strain is what we apply, and so we're showing what we do.
But strain always is defined with respect to a reference state. What's a reference state? It is changing, right? When you increase strain, you have instabilities. So it's a bit making me nervous to see plots as a function of strain.
Right. No, so like I said, what we're doing is to apply strain to the system, and we generate steady state configurations. So at that level, strain is not important to me. It's just important that I reach steady states. Okay? We are doing something where we want to understand how far we had to do whatever, apply stress or strain in order to generate these structures, but that I didn't talk about.
Let's talk about it further, because it does make me nervous.
Okay?
Eventually you plot the steady state numbers, right?
Right, exactly. So that's what I'm saying. So whether I was looking at it as a function of strain is not important to me. But there are other things
you can reveal something, the looping is a function of stress, because
right.
it's a state function. So it might be shedding light.
There was another thing you showed that how the contact number changes with the density. Your data was above the frictional numbers.
Yeah.
But for which, so what friction value are you comparing with?
So no. So that's a whole. So like
because later you say your friction when the numbers change with friction and so on.
yeah. Okay. I went through this a little bit fast. When you look at frictional simulation, for any given friction coefficient, the system jams at a different density, right? So that's this parametric curve. So here is 4, which is the limit for frictional jamming, and above about 55%, our data without friction show this roughly the same parametric dependence as frictional spheres.
So what they change is the friction coefficient.
Right.
So each one is for the sphere.
Yeah.
Thank you. One more, last. Yeah.
So friction here doesn't mean like this coefficient of restitution. It's something like nonlinear to a hard like angular dynamics. It's not the same.
So okay. So except for the last 3 slides, I've talked about frictional jamming without having friction in my system, right? But in the last few slides, the model that we are looking at, in principle, can have various dissipation mechanisms. We only included tangential, right? But the model actually allows you to do damping because of normal forces, etc., which I didn't talk about, normal velocities. Yeah.
Okay. So let's move on to the next talk, which is by
Okay.
Rick Butler from University of Brno. So we thank Srikanth for a nice talk.